each of them, and we found the following results. That the derivative here was 2x. The derivative here was 3x squared. Here we got 4x cubed. 9x squared, negative 2x to the negative 3, and negative 12x to the negative 4. We wrote those down in about, what was that? I guess we could check it later and time it. It's about 10 seconds, 12 seconds maybe, maybe 25 seconds. How long it took me to write down those answers? Think about your definition of the derivative, especially one like this, x to the 4, where you would have as part of it f of x plus h, so you would have to do x plus h to the power 4 and expand it completely, and then combine your like terms, because you would subtract f of x, right, as part of the, factor out the h, because it would be the limit as h goes to 0. And simplify the whole thing and find out that the answer is just 4x cubed. This would take a long time, and that was just one of them that we did here. So now we have to look at our original equations and look at our results and see if you can come up with some patterns. What do you notice? Okay, the coefficient that you had gets multiplied by the exponent. So here we have a 3 and a 3 gives a 9. Here it's a 1 and a 4, 1 and a 3, 1 and a 2. Okay, that's one pattern that we notice. The exponent is 1 less than it was originally. So we had 2, now we have 1, now we had 3, now we have 2, and so on. Even works for the negative ones, right? We had a negative 3, 1 less than negative 3 would be negative 4. And that is the power rule. That's all it is. So what's happening is that exponent, you can kind of think of it as the exponent coming out and multiplying the number in front. And then you just subtract 1 from the exponent. It even works with ones like this. Okay? What I'm going to do for some of these is write them with an exponent. You know the square root of x is x to the half. What exponent would I have here? Well, I know it's kind of silly, but you could write an x to the 0. That would be just 1, and 1 times 5 would be 5. This would be 7x to the 1. This would be x to the 1/3. And this one would be x to the negative a half, because it would be 1 over x to the half. But if you wanted to move that exponent up, you could have x to the negative a half. So we can take a preliminary step to think of these as exponents. And then, sure enough, the rule happens the same. Y prime for this one will be 1/2 x, and if I subtract 1 from the exponent, I get negative 1/2. What happens in this next one? It's just 0. Because if the 0 comes in front, you get 0. And so the derivative of any constant is 0. Sometimes that's given as a separate rule, but it's just an adaptation of this rule. This one, if I bring the 1 out in front, I'd still have 7, but this would become x to the 0, so it's just going to be 7. Here we'd have 1/3 x. When you subtract 1, you'd have negative 2/3. So you have to practice your fractions and need a common denominator. 1/3 minus 3 over 3 would be negative 2 over 3. And same thing here. Bring out the negative 1/2, subtract 1 from the exponent, and get negative 3/2. So not only are we able to do simple powers, but now we can do all sorts of square roots and cube roots, constant numbers, and 7x just becomes 7 because each time the exponent goes down by 1 and you multiply by that number in front. Yes?
Actually, for y equals 7x, is there for me go all our life or when we multiply as the first derivative for these y?
Yes, you have known that one a long time. That's a good point. Y equals 7x is what kind of line? Well, duh. Is what kind of graph? Oh, it's a line, right? Y equals mx plus b. What is the slope of the line? In fact, for y equals 7x, it has a y-intercept of 0 and a slope of 7, so we go up 7 over 1. And if you ever try to draw a tangent to a straight line, it's hard to do to keep the line on it the whole time. But other than that, it's exactly the same. And what's the slope of the exact same line as a line with slope of 7? It would be 7. And that's what the derivative is always finding. It's always finding what these are equations of every single slope possible. But on a straight line, there's one slope that stays constant the whole time. So that's another reason you could see that with a straight line, the tangent also will always have a slope of 7. So two rules that come out of here. The constant rule, which we noticed was just an adaptation of the power rule. If you have any constant, just a single number, the derivative of that will always be 0. And then the power rule, what's happening is the exponent comes out in front, and you can see that here, and then we subtract 1 from the exponent. And now we get to introduce you to some new mathematical language stuff. Because in higher level math, mathematicians, inherently lazy, if they can avoid writing long words, they do. And this works for all real numbers n. Every single value that's possible, this will work for. Now, in mathematics, if you go into higher mathematics, you find out that you have to write for all a lot of times. I know it's only 6 letters, but because you start writing a lot of times, you make up a new symbol, an upside down A, and that means for all. Just to make life a little bit shorter. And you've seen this, right? N belongs to the real numbers. So instead of having to write this, which would take me maybe 3 seconds, I can write this in 2.5 seconds and save a half second. Very efficient. Now, if you can find the derivative of a function, and that function is just getting multiplied by another number. Here's a brief example of this. So this constant multiple rule says that if I have some function, let's say f of x is x squared. The derivative, now that we've learned our power rule, is quite easy. It would just be 2x. All this rule is saying is that if g of x was 5x squared, and you won't even add this extra step because you will automatically bring the 2 out in front, hit the 5, and write 10. But if you wanted to, you could say g prime of x right here would be the constant 5 times the derivative, which just makes it 10x anyways. But this idea goes beyond just power rule. This works for anything. That if you have a constant in front, that doesn't affect the derivative other than multiplying your derivative by that same number.